The pH scale runs from 0 to 14. Acids are on the low end of it, and bases are on the high end of it. And in the middle, neutral is 7. But why? Why is 0 through 14? Why not 0 through 20 or something and make 10 neutral? The reason has to do with water itself. The H plus ion, or the hydronium ion, and the hydroxide ion concentrations, when you multiply them together, it makes a constant. And that happens to be 1.0 times 10 to the minus 14th. This is a constant product. So as one concentration goes up, the other concentration goes down. We'll take the logarithm of both sides, the base 10 log. And the log of 1.0 times 10 to the minus 14th is simply negative 14. With logs, the number of decimal places in the log and the number of significant figures in the number are equal. We'll separate this out. And when you separate out logs, the multiplication becomes addition. That's just the way logs work. And this is still negative 14. We'll take the opposite of both sides. In a moment, you'll see why we're doing this. So make both sides negative. So the negative 14 now becomes positive 14. The reason we're doing this is because the negative log of H plus has a name. It's called the pH. And the negative log of OH minus is called the POH. And so those added together give us 14. If the solution is neutral, that means the pH and the POH would have to be the same, because the concentration of H plus and OH minus are equal. And if they must add up to 14 and yet be equal, then the two of them will both have to be 7. That's why 7 is neutral. Let's put all this together in a magic square. We'll have the pH on one corner of it and the POH on the other. When you go between the two, it's 14 minus whichever of the two you know. (14 minus the pH gives the POH, 14 minus the POH gives the pH. So if we know the pH to be 4.7 or 4.25, let's say, then we subtract it from 14. So this becomes 9.75. To go between the pH and the actual concentration of H plus, we recall that pH is by definition the minus log of the concentration of H plus. That's if you know the H plus concentration first. Here we don't. We know the pH. So we have to go the other way. And to go the other way, you take 10 to the minus pH. So on your calculator, you take 10 to the power of negative 4.25. So in your calculator, just enter in 4.25, make it negative, and then it's usually shift on the log to make it 10 to the x. So 10 to the power of negative 4.25. By the way, the 4.25 has 2 decimal places, so the number itself is going to have 2 significant figures. So it's 5.6 times 10 to the negative fifth. And that'll be the concentration of the H+. You can do similarly for the POH. The concentration of OH minus is 10 to the minus POH. And so if the POH is 9.75, 10 to the minus 9.75 is 1.8 times 10 to the minus 10th. To go between H plus and OH minus, it's 1.0 times 10 to the minus 14th divided by whichever of the two you know. I forgot to complete the square. We've got to go from OH minus back to POH. And we do this the same way we do with the other side of it. It's the minus log of OH minus. Let's erase these numbers and try another problem. Suppose you're given an OH minus concentration of 3.6 times 10 to the negative fifth. And the problem asks you to go from that to the pH. You're going to see that either way, this is a two-step process. You can take 10 to the minus 14th divided by that number to give us H plus, and take the minus log of that to get the pH. Well, that's one way to do it. But we can go the other way. We can start with a 3.6 times 10 to the minus fifth, take the minus log of that to get the POH, and then subtract from 14 to get the pH. Either way, you're going to have to take the minus log of something, but I think you'll agree that subtracting from 14 is a little easier than dividing into 1.0 times 10 to the minus 14th. So to get from 3.6 times 10 to the minus fifth to the POH, we take the minus log of that number. So in our calculator, negative log of OH minus. So the negative log of 3.6 times 10 to the minus fifth. And that gives us 4.44. If you just take the regular log, it ends up being negative 4.44. So it's the minus log, so you flip it and make it positive. And then it's a simple matter to take 14 minus that 4.44, and that gives us the pH 9.56. It's basic. And that's because the OH minus concentration is greater than 10 to the minus 7th. If you have a strong acid, the problem is actually pretty easy. No ice tables or anything fancy needed for this one. There are not very many strong acids. In fact, there's few enough that you can memorize them. HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HClO4, which is perchloric acid, HNO3, which is nitric acid, and finally, sulfuric acid, H2SO4. This one's kind of a special case, so I'll put an asterisk by it because it has 2 protons in it. So let's say you're given a problem where you have to calculate the pH of a strong acid, other than sulfuric acid. That one's a little harder to calculate. But let's just say 0.1 molar hydrochloric acid. Hydrochloric acid, like the other strong acids, breaks down completely to give us H plus and whatever the counter ion is. In this case, it's chloride. Which means that the concentration of H plus is given by the fiendishly complicated equation It's equal to the concentration of HCl. So in this case, it was given as 0.1 molar. That's not so bad, right? So we're going to go to our magic square. We know the concentration of H+, point to it there, and we need to find the pH. There it is. And to go from one to the other, we use the minus log of H+. So in our case, we're going to take the minus log of 0.1, which is the concentration. And we do that on your calculator. Try this yourself. You're going to find that it's 1.0. 1.00, 2 decimal places, because the H+ concentration itself had 2 significant figures. We talked about strong acids, but what about strong bases? First, how to recognize something is a strong base. Most hydroxides are not soluble, but some of them are, and the ones that are soluble are strong bases. I'm writing them in order of where they would appear in the periodic table. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Those would be the first column, the alkali metals. And then barium hydroxide, but barium's 2+, so you need 2 hydroxides. And strontium hydroxide. The ones above it, like calcium and magnesium hydroxide, they're not soluble enough to be considered strong bases. So those are the strong bases. Let's say you have a problem where you have 0.25 molar barium hydroxide, and you need to find the pH of that. So this is the way you do it. First, write out the equation. Barium hydroxide breaking down in water to give you barium ions and hydroxide ions. 2 hydroxide ions, because there's 2 in the parentheses. So that means if you start with 0.25 molar barium hydroxide, we'll do the crisscross factor label method and cancel out the barium hydroxide. There's a 1 implied in front of the barium hydroxide, but there's a 2 in front of the hydroxide. So that tells us that the molarity of barium hydroxide needs to be multiplied by 2. So this is going to be 0.5 molar hydroxide. Now how do we go from that to the pH? Let's go to the magic square. And so let's say we start with our 0.5 molar hydroxide. We're going to get on our calculator, take the minus log of 0.5. So if you take the regular log of 0.5, it'll be a negative number, so the minus log of that will be a positive number. And you'll find that it'll be about 0.30. And then we just subtract them from 14, and that gives us a pH of 13.7. It's very basic. That's for strong acids and bases. Now what about weak acids? Let's say you have some acid whose formula is HA, where H represents the H+, the acidic hydrogen, and A represents the rest of the acid. And this breaks down, just as a strong acid does, to the H+ and the rest of the acid, but it's shown as an equilibrium arrow going both directions because the reaction doesn't go to completion. Because it doesn't go to completion, it's an equilibrium that's characterized by an equilibrium constant, which is much less than 1. Let's say you have some concentration of the HA that's given. That's the initial concentration of the acid. And initially, the amount of hydrogen ions and H- is 0 because the reaction hasn't happened yet. Well, for the hydrogen, it's about 0. It's actually 10 to the minus 7th because water itself breaks down a little bit, but we can ignore that. Some of this acid is going to dissociate. We don't know yet how much. But it dissociates into H plus and the rest of the acid, the conjugate base. A minus is called the conjugate base of the acid. All the coefficients are 1, so we don't have to square or double any of the x's. If there was a coefficient of 2, we'd have to double something. We'd have to put 2x. And so in the end, we have some of the acid left. X is going to be less than C. This is called an ice table because you have the change in the equilibrium line. The Ka is given in the problem. It's a characteristic of the acid. And it's X times itself, the products, X times X or X squared, divided by the reactants, just like within a equilibrium. It's products divided by reactants. The problem is that to solve for X with this, it looks like a quadratic equation. So we're going to make an assumption that X is much less than C. The amount that dissociates is much less than what you started with. So that C minus X is approximately equal to C itself. This simplifies the equation. But this is only true if it turns out that after we solve for X, that X divided by C is less than 0.05 or 5%. So if it's true that X divided by C is less than 0.05, we can make this simplifying assumption. And this simplifying assumption is that X squared divided by the concentration is Ka. By removing the minus X in the denominator, it's no longer quadratic. Cross multiply to get X squared, and then take the square root. So the square root of the concentration times Ka is going to be X. And X is the concentration of H+. That's the important thing. So once we have the concentration of H+, we use the pH square that we used earlier to find our pH. So let's say we have a problem where we need to know the pH of 0.1 molar acetic acid, whose formula is HC2H3O2. And the Ka value is given. It's 1.8 times 10 to the minus fifth. Remember, K values have no units. We'll solve this one in blue. So using that formula, the concentration being 0.1 times the Ka value, 1.8 times 10 to the minus fifth. We're going to multiply these two numbers together and then take the square root. And that'll be the concentration of H+. Get our calculators out. And it's 1.3 with a check digit 4 times 10 to the minus third. So we get this H+ concentration of 1.34 times 10 to the minus third. We need to compare it to our original concentration to check if the X divided by C was indeed less than 0.05. If so, then our assumption to ignore X in the denominator was in fact valid. So we'll check. 1.34 times 10 to the minus third on the top of the fraction, our value of X. And we'll divide this by the original concentration, 0.1. And it turns out to be 0.013, two significant figures. and that is indeed less than 0.05. So we are finished with this problem. The assumption to ignore x in the denominator was indeed valid. So we're going to plug that into our square. It's a concentration of H+. 1.3, check digit 4, times 10 to the minus 5th, or 10 to the minus 3rd. We're going to keep that 4 there in our calculator, but in the end, we're going to round the number to two significant figures. So we'll plug the 1.34 times 10 to the minus 3rd in the calculator and take the log of that number and then flip the sign to make it positive, the minus log of that number. And this gives us a pH of 2.87, two significant figures, so it's two decimal places. So let's say you have a problem where you cannot ignore x in the denominator. What is the pH of 0.1 molar HF? And the Ka is given. Notice it's greater than the Ka we had before. So we solve x squared over c minus x is the Ka. Just like we had before. And although we don't know yet that we cannot ignore x, we're going to ignore it anyway in the denominator. We'll just assume that c minus x is about equal to c. And we take the square root of Ka times c. Ka times c, then take the square root. And that gives you what x is. We'll put the numbers in. Ka is 0.1 times 10 to the minus 4th, and c is 0.1. Sorry about switching the order there. So we get our calculators. X is 8.4, check digit 3, times 10 to the minus 3rd. And we're going to check to see if that is small enough compared to c, which is 0.1. So the rule is x divided by the original concentration, and to see if that's greater than 0.05. So we take our x that we've got and divide it by 0.1, the original concentration, and it's 0.084, which is greater than 0.05, greater than 5%. So no, we cannot ignore x. So what do we do? Well, we could solve the quadratic formula, but that's a pain, so we'll do another method, which is called successive approximation. We'll take a new x, and I'll write that as x prime squared, divided by c minus the old x equals Ka. And so the c is 0.1, and we're going to subtract the x that we just got, the 8.43 times 10 to the minus 3rd. So 0.1 minus the 8.43 times 10 to the minus 3rd. Then cross multiply with Ka and take the square root. So if we just do the subtraction first, 0.1 minus the 8.43 times 10 to the minus 3rd, minus the original x, we get 0.0916. And then we'll plug in the value for Ka. Remember, that's 7.1 times 10 to the minus 4th. That was given. Cross multiply these numbers, and then take the square root to get x. So our new value of x is 8.0, check digit 6, times 10 to the minus 3rd. And we see it differs significantly from what we had before. So we're going to plug it in yet a third time to see if the value converges. So we'll get a new value of x double prime, divided by the original concentration minus the first x prime. So we're going to take the concentration, which was 0.1. Remember, that was the concentration that was originally given in the problem. Right over here, that's C. And then subtract our, this is what our second value of x, 8.06 times 10 to the minus third. And that's what goes in the denominator, the difference between those two numbers. So 0.01 minus 0.1 minus 8.06 times 10 to the minus third. And that gives us 0.0919. Then we cross multiply it with Ka and take the square root to get x double prime, the third value of x. And we're going to compare the x double prime and the x prime. So after we cross multiply and then take the square root, and this x double prime comes out to 8.0, check digit 8, times 10 to the minus third. So that did not change in the second significant figure. It changed with the third, but that doesn't matter. We only need two significant figures in the result, because the concentration and the K only had two significant figures. So the square tells us we take the minus log of that number, minus log of 8.08 times 10 to the minus third. Remember that number has only two significant figures. The second 8 is just a check digit. So since the number had two significant figures, the pH has two decimal places, 2.09. Sometimes you have to calculate something called the percent ionization. And you might encounter this in a problem where you can ignore x or when you cannot ignore x. And that's just the x divided by the concentration times 100. So in this case, we take our x, which is our third value of x double prime, the accurate value of x, 8.08 times 10 to the minus third, divided by the original concentration that given in the problem, which was 0.1 times 100. And that gives us 8.1%, two significant figures. And that's greater than 5%. Now, some people would get misled into thinking that's somehow wrong, that we cannot ignore x in the denominator because it's greater than 5%. Well, we didn't ignore x in the denominator. We plugged it back in and solved the problem a couple times. The purpose is not to get the percent ionization less than 5%, but just to get a more accurate value of the percent ionization. So at this point, it's okay that it's greater than 5%.